Okay, hello people watching this video. This is the continuation of 5.1. We are on the second page. I went ahead and just said skip this formula. It talks about probability tables and stuff up here, but I think it's just easier to look at the table. So we're not going to worry about bogging you down with the formula because it's just disgusting. But I do want to talk about this notation for 0 plus, okay? We talked about this before. When you have a probability that's like really small, like I think we said your rate of, let's say, dying when you skydive. So dying when skydiving. Okay. In the past, out of the, let's say, 1 million people that have skydived, I don't know. What's that word? Skydived? Yeah? Out of the 1 million people that have skydived, I don't know if that's even a word, there were 4 deaths. Okay, 4 people died out of 1 million. If you convert that to a decimal, I don't know if anybody got that number. Somebody want to divide that for me real quick? I have a calculator out. 4 divided by 1 million. A really big negative number, I guess. 0.00 something. If you take 4 divided by 1 million. Out of the 1 million people that skydived, 4 of them died. What? 4 to the negative 6th power, okay? So that is 0.000006, okay? So that number is a number that's awfully close to 0. Like it's next to impossible. 6, not 4. 4, 6. 4. Thank you. It's next to impossible that that's going to happen, but it's not impossible. So if we round that thing, we don't want to round it and say that that's 0, right? So a lot of times what they'll do is they'll say, instead of saying that decimal, they'll say 0 plus, which means it's a number that's really close to 0, but it's not 0 exactly. It's not impossible that's going to happen. It's just very rare. Does that make sense? Okay, they'll just say 0 plus when it's a really spaced out decimal number that's really close to 0, okay? That type of thing, okay? Job interviews, we talked about this yesterday about how this cannot be a probability distribution because it's over 100% or over 1 as a decimal, right? We can't have probabilities that add up, or that table that adds up to be more than 100%. Happy with that? Okay, now, the next task that we have to worry about is when we have this table. This is the coin toss table, so heads and tails, and specifically we're talking about heads. We usually choose one, right? We're talking about 0 heads, which means, I'm going to put in parentheses, 2 tails, 1 head, which means 1 tail, and 2 heads, which means 0 tails. That's kind of like the other side of the table. That's what that means, right? That combination happens 25% of the time, 50% of the time, 25% of the time, right? Why does 1 head occur with a higher frequency than the other 2? Heads, tails, heads. They're not counting like order mattering, right? So they're saying heads, tails is the same thing as tails, heads. It doesn't matter, right? So that's why it's 50% instead of 100, all right? Now, we have to use this table, and I'm going to say that if I flip a coin, what's the average number, or let's do the mean. The mean number, looking at this table, we have to use this table to find the mean, right? Okay, well, how do I find a mean when I have like a whole table? Like, I can't just do like one thing, right? How do I find the average number of heads if I just have a table? Like, I have all of those things. Like, I have 6 numbers in there. How do I do that? I don't know. Here's how you do it. So the outcome was X, okay? And this is happening 25% of the time. So here we do 0 times 25. This is kind of like when you're weighting your classes, right? Like you have one grade that's 25%, one grade that's 50%, one grade that's 25%, right? And you scored a 0, a 1, and a 2. You're going to multiply those together, right? 0 times 0.25, 1 times 0.5, and 2 times 0.25, right? Okay? So 0 times 0.25 is just going to be 0, right? 1 times 0.5 is just 0.5. 2 times 0.25 is 0.5, and I add those together. 0 plus 0.5 plus 0.5 is 1, right? And then usually when you're doing an average, you're dividing, right? You have to divide by the total amount. But if I add these probabilities together, what happens? You're just taking and you're like really dividing it by 1. Does that make sense? And that will always be the case. So you really don't even have to divide after you've multiplied because it will always end up being 1 in a probability table, right? Okay. So this means that if I flip 2 coins, the average number of heads that I will get on average will be 1. Does that make sense? That should make sense, right? Okay. So the mean there is 1. They're saying over here for the formula, they say you take all of the x's times the probability. That's what we just did. You take all of the x's times the probability that it's going to happen. So this was like 0 times 0.25, 1 times 0.5, 2 times 0.25, etc. And we add them all together. That's what this guy means, the sum. You take the sum of all of them. And we got 1, right, for this problem. That's how you find the average. When you have a probability table, finding the average, you just multiply those together and add them all up. Does that make sense? That's the only option that you have. What's up? Come zoom out. Okay. Oh, zoom in. There you go. I just wrote down 0, 0.25, 1, 0.5. You don't necessarily have to write that down, but just kind of showing you from the table, that's where we get that. Okay. Now we also have standard deviation and variance that we're going to do. Okay. And they have formulas for those down below. That's what we're going to do next. So we have variance and we have standard deviation. And just kind of like they did before, they gave us 2 tables or 2 things to do, right? They use, I think, this one more often. They use this guy more often. I'm going to circle him. This is what they use for variance the most often. Let's go through and let's figure out what these numbers are talking about. Like, what does X stand for? What? What is the X standing for? Like, according to our table. X was the what? The number of heads. Okay, so I'm going to run it right in here, the number of heads. Okay, P of X, the probability of getting that number, right? And what is this guy? What's he called? That little symbol. Do you remember what he is? What is that little thing? It kind of looks like a U. It's mu. Yeah. Do you remember what mu is? Mu is another symbol that we use for mean. It's the population mean. Okay. So we've calculated the mean. The mean is 1. Okay. So we're going to fill that stuff in. All right. We're going to calculate the variance and the standard deviation below in this table. Okay. All right. I'll go up. So we're filling all parts in there. And then to go from standard deviation, or from variance to standard deviation, how are those 2 things related? If you have the variance, how do you find the standard deviation? You take the square root, right? So these 2 guys, one is the square root. Okay, you have the variance, you take the square root to find the standard deviation. That's all. Okay, good? All right, perfect. Perfect. Are we ready for example 3? Okay, all right, they want us to find the mean, variance, standard deviation of this table with the heads and tails, like the one that we've just been dealing with. And they want us to, they used the first formula. Poop, that's okay, whatever. We already found the mean, right? The mean off to the side, we did that at the top. They're calling mu equal to, what did we find? 1. The mu is 1. Okay. All right, they're using the top formula for variance of the 2. Okay. So in the variance formula, they want the sum of all of the x's times the p of x's. Okay. So we're going to take x times p of x. Okay, so I'm going to multiply those 2 together just like I did when I was finding mean, right? X times p of x, whatever, okay? This guy, yeah, this guy is finding the mean, yeah. So mu is equal to 1. We've done that already. I'm not going to fill that table in because we did it up above. Okay, but then they want us to find the variance using this stuff, okay? So we're going to do all of the x's minus the mu's. We're going to square that, and we're going to take it times p of x, okay? And then we're going to sum all of them and add them all together. So we're just filling this table in, okay? So the first thing that I'm going to put is my first x. What's my first x? 0 minus mu, which is 1. I'm going to take that guy and square it, and I'm going to multiply that by 0.25, which is p of x, okay? We're going to figure out what that guy is. Let's go ahead and fill in the other numbers, and then we'll just do all our calculations. So my second x is 1 minus the average, which is 1. And we're going to take that guy times 0.50 or 0.5, right? The next number is my third x, which is 2 minus the average, which is 1, squared times 0.25 again, okay? And this is, after I add those all together, that's going to give me my variance, okay? So this is not terribly difficult, I don't feel like. If we do some math here, 0 minus 1 is negative 1 squared, is positive 1. Positive 1 times 0.25, 0.25, okay? 1 minus 1 is 0. 0 squared is 0 times 0.5, still 0, right? 2 minus 1 is 1. 1 squared is 1 times 0.25, 0.25 again. So the variance is going to be 0.5. This is my variance. I feel like when they do these, the formula looks a lot more intimidating than the actual process is. Like, that wasn't terrible, I don't feel like, right? Okay, so that's finding the variance. And then let's go ahead and do the standard deviation. Okay, so the standard deviation then would be, how do I find it? The square root of 0.5, yeah, okay. Square root of 0.5, something like 0.707. No, wrong. 0.707. Is it really? Ha! Yeah, it's the square root of 1/2, which is a trig thing. Anyway, 0.707. That's the standard deviation. How is it that standard deviation is bigger than the variance? Like, isn't standard deviation the square root? So shouldn't it be a smaller number? When you take the square roots of decimals, you get a bigger number. Did you know that? Yeah. If you take the square root of a whole number, like the square root of 4 is a smaller number, which is 2. But if it's a decimal number, like a number less than 1, it's going to end up being a larger number when you take the square root. Okay, so standard deviation, 0.707. All right, we've talked about significantly high and significantly low values. If you have the average, okay, so let's do this. Let's say I'm going to do, I can't do heads and tails in this because this doesn't make sense. Let's do 85 is your average, okay? And the standard deviation, let's say standard deviation is 5, okay? So this is a test. We're doing a test, right? What's considered to be a significantly high grade on that test? You're adding 2 standard deviations. So if I add 5 and add 5 again, that high number would be anything larger than a 95. So you scored significantly high on this test if you scored anything higher than a 95, okay? You scored significantly low on the test if you scored anything below 75, right? If my standard deviation is 5, 75 is the cutoff mark for what's considered to be significantly low. Do you guys remember doing this when we did like height? And we talked about India. Were you significantly low height? I don't remember. And then we talked about Abigail, I think. I don't remember if you were significantly high or not. I don't know. Anyway, we just did 2 standard deviations on either side, right? And if you're outside that region, then you're considered significant. What?
I'm average height.
You're average height? Okay. Whatever. Anyway. Okay, good. All right. Identifying significant rules with the range rule of thumb. It said that we found that when tossing 2 coins, the mean number of heads is 1. And the standard deviation was 0.7, right? 0.707, okay? So let's figure out our, this doesn't make a whole lot of sense, but anyway. Let's figure out what's considered to be significantly high and significantly low for the number of heads to get, okay? 2 is here in the middle. And I'm going to add twice and I'm going to subtract twice, okay? No, not 2 in the middle. Why is 2 in the middle? Not 2 in the middle. 1 is in the middle. 1 is the average, right? Mu equals 1, okay? You add 0.7 twice. So, 2.4, right? Is it 2.4? And then, if you add 0.7, it's 1.7. Add 0.7 again, it's 2.4. Yeah? Did I do that right? Okay, if you subtract 0.7 twice, negative 0.6, negative 0.6. Okay, I don't like this problem. That's why I switched it up above and didn't use heads and tails. So this says that it's considered to be a significantly high number of heads if I would roll anything, or if I would flip anything more than 2.4 heads? Negative 0.4? It would be 1 minus. Oh, yeah, negative 0.4. You're right. You're right. Okay. I don't know. I can't math today. It's Friday. What? If you take 1 minus 0.7 and then minus 0.7 again. Yeah, negative 0.4. Yeah. So this is saying that it's considered to be a significant number of heads, or a significantly high number of heads, if I would flip 2.4 heads. Out of how many? 2 to begin with. I don't like this problem because it's not like, it doesn't make a whole lot of sense, right? Okay, so I don't know why they put this in here, but it's good to like practice the adding and subtracting, okay? They're saying it's considered to be a significantly low number of heads if you flip anything less than 0.4, negative 0.4 heads out of 2. Can you flip a negative 0.4 heads? I don't like this problem, right? They needed to use a different context for this problem. But anyway, getting to that point, you know, it's the same process. Realistically, this doesn't tell me hardly anything. So I guess maybe it tells me that the entire, like all of the set of possible outcomes is I could get 0 heads, I could get 1 head, or I could get 2 heads, right? And those 3 combinations fit entirely inside of what is considered not significant, right? Like this is the non-significant region, okay? So if any of those combinations show up, it's not really like a wow factor to me, right? So I guess that's kind of maybe the point that they're getting across here, is that any combination, I could get 0 heads, 2 heads, 1 head, all of those are not significant, right? Those are common things that could happen if you're flipping 2 coins, okay? Not out of the range, okay? Okay, let's go on down. Also, if they give you probabilities, it's considered to be significantly rare if it's, I'm going to write that down over here. Significantly rare equals less than 5% chance of occurring. Okay, you had 2 questions like that on your review for chapter 4, and I think you had a question like that on your test maybe, right? It's considered to be significantly rare if it has a less than 5% chance of happening, right? That's just kind of what we know, right? Either it's 2 standard deviations on either side, or it's a less than 5% chance of happening, okay? That's kind of how that works. Happy with that? Mm-hmm. All right, identifying, we have, oh man, okay, here we go. Example 5, is 252 heads out of 460 coin tosses considered to be a significantly high number of heads, okay? So let's talk about what the split should be. 460 is how many things I am flipping, and of that, how many heads should I get, assuming that this is a 50-50 split? I should get 230, and I should get 230, right? They are saying if you get, for, what are we doing, heads? They are saying if you get a 252 heads, how many tails would that be? Like 208? Is that a significant split? I don't know. That's kind of in like the middle range where I'm like, are we starting to get into like crazy splits or not? Like, what's the chances that happen? Okay. So they have calculated the numbers, and we'll talk about how we calculate these numbers later on in the chapter, okay? They have said, they've crunched the numbers, and they said that 252 out of 460 occurs with the probability of that. Okay, that's the probability of getting a 252-208 split. So is this significantly rare? Yes. It is a significant split to have a 252-208 split exactly. That's kind of getting to that crazy range, okay? So yes, significantly rare. It is rare to have that happen, a 252 out of 208 split, okay? Because that decimal number is less than 5%, okay? Make sense? All right, let's go down to the next one. Expected value. These are like we're gambling problems. Okay, All right, you have $5 to place a bet in the Golden Nugget Casino in Las Vegas. You have narrowed your choices to one of two bets. You can either bet in roulette or you can bet at the craps table. Okay, so you're betting on the number 7 in roulette, and I think in roulette there's 38 slots. Okay, so in roulette, if you bet on the number 7, you have a 1 out of 38 chance of winning, right? 1 out of 38 is your win chance. The chances of you losing is 37 out of 38. That's the chance that you're going to lose. Okay? But if you, let's see, bet on the pass line in the dice game. I got to read this because I don't know what the pass line is. Let's go down here. Let's talk about pass line. Pass line, the probability of losing is 251. So the probability of winning is 244. 244 out of 295 equals a win, which means your probability, 495, not 295, 495. 244 over 495 is a win, and 251 over 495 is a lose. Okay? So, which one do you have better chances of winning on? The craps, right? Because that's almost a 50-50 split. Not quite, right? But it's almost a 50-50 split. Win-lose, right? 495. Yeah, I'm going to fix that number. Okay, you have a better chance of winning at the craps table. But how much are you going to win? A lot less than if you would win in the roulette, right? So roulette, you have a very, very slim chance. 1 out of 38. That's kind of a low number of chance of winning at the roulette table. But you're going to win a lot more than if you would at the craps table, right? Okay. So we're going to talk about like the chances of you winning and how much you would win, etc. Okay. So we're going to find your expected value. Okay. Like what you can expect to happen on average. Expected value is like your average number. Okay. The average value. So if they say average value or expected value, those mean exactly the same thing. How much you can expect to get out of that bet, I guess, okay? You are betting $5, okay? And you're betting $5 in either one. So we're going to look at scenario A, which is at the roulette table, and then we're going to look at scenario B, which is at the craps table, okay? So they've set up a table, and they've said if you lose, you are going to lose $5, right? If you win, you are going to win $175 net, which actually means you're getting $180, but 5 of it was yours to start with. Does that make sense? So you're netting $175. They had to put that in there just so that it's clear, okay? So you're going to win $175. That's big, right? But your chances of winning are very small, okay? So they've set those as my X's. I'm going to lose $5 or I'm going to win $175. My chances of losing is 37 over 38, and my chances of winning is 1 over 38, right? And then all we're doing is we're calculating the average or the mean, right? When we have a probability table to calculate the mean, we just take these times each other and add them together, right? Okay? So they have taken negative 5 times 37 out of 38, which is negative $4.87-ish, right? Okay, then they said, let's take 175 times 1 over 38. You're just taking the X times the probability, just like we did with the heads and tails. X times the probability, X times the probability. And what happens here is we add those two together and we end up getting negative 0.26. Okay, so what this means for expected value, this means that if we play over and over again, play a lot, if we play this game a lot, over and over again, we can expect it to average out to me losing 26 cents every time I play, right? Because the number of times that I win, even if I'm winning 175, I'm going to lose that many times to cancel that out, right? And it's going to average out to me losing 26 cents per game, right? So, moral of the story, if you go and sit down at that table and you win, you walk away, right? Because you're probably not going to win again for a while, and you're going to lose a bunch in a row, and you're going to end up losing your $175 because it's going to average out to be negative 26 in the end, right? And that's all going to the casino. Like they're making 26 cents off of you every single time you sit there. Yeah, sometimes they have to pay out $175 to you, but on average, it's going to cancel out so that you are losing 26 cents every time. That's the average. So if you play a lot, you are lose 26 cents for each game. And that's the average. Okay, you are averaging out to be negative 26 cents per game. Okay, if you keep playing. So if you go and play and win, get out. Okay, all right. B, let's look at the lose-win. Okay, so if you lose your $5. If you win $5, which means you actually have $10 now because 5 of it was yours to start with. Okay, your chances of losing is a little bit higher than your chances of winning, right? But it's almost a 50-50 split, almost, okay? So here, if you multiply those together, again, we're finding the average. So if we multiply those together, we get negative 2.53. If we multiply these together, we get positive 2.46. But in the end, it's still, like, we add these together, we take the sum, we add them, okay? And that gives us a negative 7 cents. So here, if we keep playing over and over again, if play a lot, you're only losing 7 cents every time you play, right? You're losing 7 cents on average each time. Every time you play, you're losing 7 cents on average if you average them all out. Does that make sense? So no matter what, you are going to lose money if you keep playing over and over and over again. Which one is the better deal, though? Craps, but you're still going to be negative. So it doesn't, I mean, whatever. They set it up that way because they're trying to get money from you, right? If you were positive going to the casino wouldn't exist because they wouldn't make money, right? They have to set it up that way so that they're making money, right? So if you win, get out. Because if you keep playing, on average, it will cancel everything out and you will lose $7 on average, right? Okay. So you have narrowed your choices down. Did they ask? You have whatever. Which one is the better bet? Play craps? Maybe. If you're going to play at all, play craps. And neither one is a good choice, but play craps. Okay? Even though you're still losing money. Don't play at all if you're in, whatever. Make sense? Good? Okay, so that's expected value. It's like finding the average. You just set up the x's, set up the probabilities, multiply them, and add them together, just like we did with the heads and tails. Okay? All right, good? All right, bye people in the video.